Okay, so in the previous block, we saw dependent types, and dependent types is only half of the difficult material in this lecture. So lecture 3 is really one of the toughest of the whole course, maybe the toughest. So don't worry, again, let it sink in if it doesn't sink in, if you don't get everything immediately. So dependent types, we saw, allow you to have a dependency between the value passed to a function and the type of the result. And now what we're going to reveal is very connected to that. It's a bit of a mystery. It's something that you might have noticed already, which is that there are two worlds in Lean, and those two worlds look very much the same. For example, you have in the types, you have the arrow, this kind of arrow here, right? Let's do it with the keyboard. This is the function arrow. So you can create function types using that, but this is also the implication symbol. And we now saw that the for all symbol is used both for dependent types and also for universal quantification. So we see that there's some kind of overload, sorry, not overlord. And you see that the same notations are used for two different things. We've also seen the colon operator, right, which is used both for when you specify a lemma, then you say, well, I want the lemma to be called HA and the proposition is A, and then you put a colon between, but it's also used for types, right, to say that a certain variable or term has a certain type. So also the colon is overloaded in the same fashion. So now the big revelation here is that these two parallel universes, the types on one side and the propositions on the other side, it's not just a coincidence that they look the same, because in dependent type theory, or at least the dependent type theory implemented in Lean, they are the same, right? So this is the moment of the course where Darth Vader tells Luke Skywalker, I am your father, which of course is not a surprise to any Dutch speaker, given that his name is literally father. But anyway, if you don't know which movie I'm talking about, it's called Star Wars. It's I wasn't even born, I think, when it came out, but you might have heard of it. Okay, jokes aside. Okay, so what I've basically tried to say is the PAT principle, trying to state it, which says that propositions are types. Propositions are just types like any other. And PAT is a double acronym or a mnemonic. It also stands for proofs as terms, right? So, the terms inhabit the types, and in the same way, the proofs inhabit the propositions. And not only that, well, the proofs are terms. There's, as Lean uses the same syntax for proofs as for terms, and because they are the same thing. And we saw it earlier, right? We were passing, an argument to a lemma, just as if we had been passing an argument to a function, because lemmas are functions, because lemmas are terms, right? So the good news about the PAT principle is that you can go a long way without understanding it. You can just imagine that those are two separate universes, that they happen to look like each other, and that they never mix, and you live a long and happy life and be able to do all sorts of things in Lean. You'll notice, I can use check both for lemmas and for terms. Oh, I can use this and that for both. And you will start thinking, that everything in Lean is duplicated so that it works for both. And what Pat is telling you is like, no, the implementers of Lean were too lazy. They didn't do everything twice. They did it once. Okay, so all of this is still a bit abstract, but think of it a bit more concretely, right? So why shouldn't a proof be a term, right? What is a term? A term is basically a tree, right? You have f, which is a function which is applied. You have a parse tree associated with a term. And what is a proof? Well, a proof is typically represented as a tree as well as a data structure. Terms can be used to represent values of data structures. So why not use terms to represent proofs when we have them? So it's a very natural idea. As for the idea of using types to represent propositions, that's a bit more subtle, but I mean, if you admit that there's a parallelism between, terms and proofs, then you might be willing that the same parallelism exists also at the level of types and propositions, right? The type of a term tells us, this particular term is part of this larger set of things. And same thing with proofs. It tells us, well, this proof here is, part of the possible proofs of that proposition, right? The set of all proofs of that proposition. So I'm going to show this Curry-Howard correspondence, as it's called. Sometimes it's called Curry-Howard-de Bruijn, especially in the Netherlands, but I have difficulties pronouncing that noun, so I'm just going to call it Curry-Howard correspondence, like most of the rest of the world. Also, I'm not Dutch, by the way, in case you haven't noticed. Right, sometimes it's called the Curry-Howard isomorphism as well, so it has different names. So Curry and Howard were two separate gentlemen. That's why there's an N dash in between. Okay. So let's go slowly through the implications of the PAT principle or the Curry-Howard correspondence. So purists will distinguish the two slightly, but in the course we'll use the two as synonyms, because in Lean there are synonyms, PAT and Curry-Howard. Okay. So first let's start with the types, right? So this we all know. This is a type of total functions from sigma to tau. This is the dependent function type from sigma to tau x, right? Where you can have a different x depending on the value you pass of type sigma. That's what we saw. That's why we just covered dependent types, so we can talk about them here. And now let's look on the other side of the mirror, right? Or the dark side, if you want, or whatever. I mean, whichever metaphor you like. So propositions. Well, let's suppose that P and Q are propositions. Well, this is an implication, right? This is P implies Q. But here's another way to look at it. You can also think of it as a function type, really, right? And this here, well, this is the type of proofs, of the property T. So what this is telling us, if we look at it in a computational way, so as a computer scientist, we say, well, this is obviously the type of function that take a proof of P as argument and returns a proof of Q, right? And if you're able to exhibit a function that does exactly that, that takes an arbitrary proof of P and turns it into an arbitrary proof of Q, then that means that P implies Q. Otherwise, you would not be able to do that, right? So that's the essence of the Curry-Howard correspondence. And then, and I think some of those ideas go back to people before Curry and Howard. So I'm not trying to trace the history of the concept. I think Brouwer was involved in this, another Dutch name I'm trying to avoid pronouncing. There was a gentleman called Kolmogorov. I hope none of my colleagues see me mispronounce his name and probably put the letters in wrong order. I'm really sorry. So I'm not trying to trace the history of it. But what I'm trying to say is in 20th century, various people have discovered that there were some correspondence between logic and computation. But this is not very much a focus of discourse. Here, we're trying more to focus on practical theorem proving. Still knowing a bit of theory helps in the process, and this is what we're doing today. Okay. And now we see this is the for all, and this is the for all we're all familiar with, but we see it has the same, again, has the same syntax as for types. It's the same idea. I've just used different meta letters just so that we feel at home, that we see, oh yeah, this might be a proposition, P and Q, that sounds reasonable, but ultimately it's the same as above. And again, you can read it literally as logic, for all x, Q of x, or you can take it as the type of functions, that take a sigma argument that we'll call x, and that return proofs of Q of x right? So terms of that type, right? Proofs of that propositions, that's the same thing, right? So basically you give an X and it gives you the proof for that X. You give another X and it gives you another proof for that X. This is what a for all is, right? So if you manage to prove something for all X, that means you're able to exhibit a proof for every single X, which is exactly what we're doing here. It has a very naive, simple, intuitive understanding, right? As a program, a very short program, right? I mean, the program, instead of just enumerating all the proofs, you know, Q of 0, Q of 1, Q of 2, and so on, just says, well, give me an X and, you know, and at that point, I'll give you the proof. But until you query me, I'm not going to give you any proof. Okay? Sorry. So this is types and propositions, and I've said they're kind of the same, and we see, especially with the second meaning here, that they are the same. You can see that propositions are a special case of types. And then we see the same thing happen with terms and proofs here, right? So what are possible terms? Well, we saw that a constant is a term, a variable is a term, a binary application is a term, and a lambda expression is a term. And then we see with the proofs, we have the same story. So we have that a lemma or a hypothesis name is a proof. So it's a bit like a constant or variable. You have, you know, if you have a lemma name or hypothesis called big H, and then you pass an argument, well, and there's a leading quantifier for all, well, this will instantiate the for all. And we've done that before as well. And then sometimes what we have is an implication, and what we do is modus ponens. And this is what this syntax does as well. It's also an application. It's really just the same as here, right? Once we understand that the arrows are, the implications are actually just function types, right? So H will be of a function type, and then we pass the an argument of the right type, and we obtain the result. That's, you know, modus ponens, or function application. It's the same thing, right? Then we have two more cases here which correspond to lambda. So so let's see. You have this one is a bit more subtle. I think I need to turn on my brain first and get some water. I must say, don't worry too much about these. So I think they're almost more confusing than helping. So if you don't get them, I mean, I always have to stare at them quite closely before you come back to me, but let's try nonetheless. So we have an assuming, right? So if the body here is a proof of Q, well, then, you know, abstracting over with a little h of type P, that gives us a proof of P implies Q. That means, you know, if you give me a proof of P, right, and you call it little h, then I can use it and plug it into, I can use it, sorry, to give you a proof of Q by, you know, plugging that proof of P somewhere in my proof, presumably, right? So I can use the proof of P to build a proof of Q. That's what it's trying to say. It's a bit cumbersome, but it's because of this assuming here, right? I'm trying to be a bit formalistic. Like, you can think of it as a typing rule, right? So here you have extended your context with the H variable, and here you have a bound variable. So when you think like about it like this, then it's not so bad. And here you have the exact same thing, except that you're doing a lambda on some data, some value, maybe a natural number or something. So, right, so it's a for all quantification instead of an implication typically, right? So you're saying, yeah, if h of x, you know, is a proof of Q of x for all x, then you can abstract over the x, and then you have a proof of the for all. This, you know, really tells you literally, give me any x and I'll give you a proof. But again, this is all a bit formalistic here, so again, don't worry too much. I'm not going to ask you at the exam to write anything that resembles that. Okay. And well, here we have some examples of what I call raw proof terms, right? So instead of writing structured proofs, we can also write, use the lambda calculus directly to write proofs, right? So here we'll think in terms of programs. Actually, I'll just comment this out, and we'll rediscover it. Why is my keyboard not working? That is a bit worrying. Some keys are working and others are not. Let's see. Oh, now it's back. That's a bit reassuring. It's the only laptop I have in this country. Okay, I'm going to put a sort. No, wait. So we start. No tab completion. Thank you. So what we have, apart from the little bubble, I guess, is we must find an inhabitant for this function type, right? And there you see wax in, wax out coming again, right? So we need to find an inhabitant for this type. Is the same as we must write a proof for this proposition. So we're going to do it that route. We're going to use the the algorithm that was presented in the first lecture. So we see, okay, the root symbol is an implication, so we're going to start with a lambda, right? And then we're going to call it, I'm cheating, right? I'm looking at the line below. Oops, just go and B. And now we see, okay, what do we need to continue? Well, actually, we don't need to cheat really, right? Can't do it like seriously. Okay, we have B and A is what we must prove. I think we can start with that. We're going to say, let's prove B and then let's prove A. So that is going to be an intro, right? And then it continues. We need to find a B, and we have A and B. So we're going to use an elim right of HAB, and here an elim left of HAB. And that's it. You see, what I've done is type inhabitation, except that now we have extra functions that we can use, right? We can use any function we have, and not just those that we had in the first lecture, which were provided in the environment. In the local context. So, so that's how it works. And I can also do a structured proof if I want. So the lambda here is really an assume, right? And that works. I can make it a bit more idiomatic with a show, right? And then I can put the B and A. And if I find those steps too big, for example, this step here, I could say, well, let's use a have HB. Oops, sorry, B. And that's it, right? And there you see the correspondence between the lambda terms and the structured proofs, and that you can mix and match the two. There's no real difference. It's just one is just syntactic sugar for the other one, right? And here you see the tactical proof as well, right? So this is the one most people will prefer to do because it's really like a video game. You're like, okay, and intro, it gives you two goals. You don't have to put all the underscores. It keeps track very nicely of the states for you. And well, you end up sometimes with some weird variables here, but that's not the end of the world. Okay, so that's another way of doing it. And then you can even print them. And then what it does is it prints the term, right? And then you see, oh, all these, all these assumes and have and so on. When we print them, they're gone. They're just syntactic sugar. There's really, we see lambdas instead. Well, the have is there, the show is there, but the assume is just gone, it's just a lambda. Then the other one, well, you see, when we do a tactical proof, behind the scenes, Lean translates it automatically into a proof term, right? It just does, it just glues things together for us so we don't have to. And that's it. That was the Curry-Howard part. And as I said, the good news is you can go very far without fully understanding it. Nonetheless, this is, you know, a master's course at the university, so it's good if you learn a bit of theory. It's a very important concept in Lean, and it explains lots of symmetries.